Hey everyone, ever stop and wonder how your phone knows your face? Or how Netflix just knows what movie you're in the mood for? It honestly feels like magic, but it's not. It's machine learning. So today, we're going to pull back the curtain and figure out how a machine can actually learn.
I mean, that's the big question, right? It sounds kind of impossible. A machine is just circuits and code. So how do we get it to spot patterns, make predictions, and adapt on its own, almost like a person? Well, it turns out the inspiration for it all comes from a place you know very well. And it all starts right here. You see, a lot of machine learning is basically trying to copy the most powerful learning machine we know of, the human brain. This little guy, a biological neuron, takes in signals, processes them, and then decides whether to send a signal out. The artificial neurons inside our computers are trying to do the exact same thing. But, even a brain needs something to learn from.
Which brings us to the fuel for any learning machine, data. A whole lot of it. Just like we need books and life experiences to learn, a machine needs raw material to study. But what does that material actually look like?
Well, first, we give it what are called features. The easiest way to think about features is that they're just clues. They're the characteristics of something. So, for instance, if we want a machine to learn how to identify flowers, the features might be things like how long the petal is, or how wide the sepal is. These are the raw facts it gets to work with.
And if you give a machine clues, you also have to give it the answer key, right? That's what labels are. A label is just the correct answer that goes with the clues. So, for a certain petal length and sepal width, the label would be the actual name of the flower species. The machine's entire job is to figure out the relationship between the clues and the final answer.
So check this out. This is literally what the machine sees. You can think of it like a textbook filled with examples. Every single row is a different flower. You've got the features, the measurements, on the left, and way over on the right, you've got the label, the correct species. The machine's going to study thousands, sometimes millions of rows just like this to find the hidden patterns. Now here is a really, really important part. We don't let the machine just memorize the entire textbook. I mean, that's not real learning, is it? That's just cramming. So we split the data. Most of it becomes training data. That's the study guide it gets to learn from. The rest we hold back as test data. This is the final exam. It's full of flowers the machine has never ever seen before. And that is how we find out if it has truly learned the concepts.
Okay, so we've got the study guide, we've got the final exam, but what does the actual studying look like? What is this training process? Well, at its core, it's actually a pretty simple loop. You make a guess, you check how wrong you were, and then you make a better guess.
The whole goal of training is to make your error as small as possible. I want you to picture this curve like a big hill. The very bottom of the valley is the perfect, correct answer. The model starts by making a totally random guess, which lands it somewhere up on the hillside. Then it calculates how wrong it is and adjusts itself to take a little step downhill towards that correct answer. And it just does that over and over and over, basically rolling down the hill until it gets as close to the bottom as it possibly can.
But how big are those steps it takes down the hill? That's controlled by a setting that's absolutely crucial, called the learning rate. And you have to get it just right. If the learning rate is too big, the model just leaps right over the answer. It completely overshoots the goal, and its error can actually get worse. But if it's too small, it takes these tiny, microscopic steps, and training could take forever. It's all about finding that perfect balance.
So that whole rolling downhill thing, that's one awesome way for a machine to learn. But it is not the only way. You should think of machine learning less like a single machine and more like a whole toolbox filled with different models, where each tool is designed for a very specific job.
And this leads to a really fundamental idea in the field, called the no free lunch theorem. All it really says is there's no magic model that's the best at every single problem. It just doesn't exist. Why? Well, because the patterns you're looking for in a photograph are completely different from the patterns in stock market data, which are different from the patterns in language. You need the right tool for the right job. Some of these tools are wonderfully simple and transparent. A decision tree, for example, is basically just a flowchart of yes or no questions. We can literally follow its thinking right on the screen. Let's try it. We start at the top node. Is the petal width less than 0.75 centimeters? Let's say yes. We follow that path and bam, the model says it must be an iris setosa. It's super clear and you can see exactly how it came to its conclusion. But what about trying to solve really complex problems, like recognizing your face in a crowd or understanding what I'm saying to you right now? A simple flowchart isn't going to cut it. For those incredibly tough jobs, we turn to much more complex tools, like neural networks. that take their inspiration directly from that interconnected web of neurons in the brain that we saw at the very beginning.
All right, so our model has hit the books, it's passed its final exam with flying colors. So now what? Well, now we have to give it a detailed report card, and then, finally, put it to work out in the real world.
And this right here is the model's report card. It's called a confusion matrix, which sounds way more complicated than it is. Really, it's just a simple grid that shows us where the model succeeded and where it got, well, confused. That diagonal line of numbers going from the top left to the bottom right, those are all the correct predictions. Anything off that diagonal represents a mistake. It's a fantastic way to see a model's strengths and weaknesses at a glance.
So for this particular model, which was trying to predict a medical condition, we can see it correctly identified 71 healthy cases and 40 unhealthy cases. That's fantastic. It got the answer right 111 times.
But, and this is arguably even more important, look at the mistakes. It made 3 of them. It misclassified 2 unhealthy cases as healthy and 1 healthy case as unhealthy. This is so critical because it's a reminder that no model is perfect, and in the real world, sometimes one type of error is far, far more dangerous than another. So where do these graduated models end up? Oh man, they are everywhere. They're classifying smiles in your photos. They're doing sentiment analysis to figure out if product reviews are positive or negative. They're being used in drug discovery. They're modeling language for translators. And yeah, they're even trying to predict what the stock market's going to do next. The applications are just exploding. And that brings us to the big final thought. We've built these incredible learning machines, inspired by our own minds. We've figured out how to feed them data, how to train them, and how to grade their work. So the only real question left is, what are the next great challenges we should teach them to solve?